Nee, 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 nee. Ja, ja, ja. Nou, plezier, plezier. Hop. Ja, cool. Goed, goedemiddag. Ja, precies. En welkom bij deze laatste sessie tussen dit en lunch. Ik zal het proberen zo kort mogelijk te houden. Zo niet, dan is het niet mijn schuld. Ik ga het vandaag hebben over Compute by Day, VDI by Day, Compute by Night. Gebaseerd op een project wat ik in de... Oh. Yes, I'm going to switch to English because we have a couple of international guests. I'm going to talk about a project I've been working on for a while, and it's called VDI by Day, Compute by Night. And I'm not specifically going to mention the type of customer or the industry that they're working in, but stuff will eventually become clear. So VDI by Day, Compute by Night. And let me start with an introduction, that's maybe better. So my name is Johan van Amersfoort. I'm an EUC geek. I work for ITQ consultancy in the Benelux, Wijk aan Zee and in Leuven. And I primarily focus there on delivering content. So creating content, and content in the most wide form there is. So one of the things I've been working on for a while now is our Lightboard project. Any of you seen any of these videos? Quite some hands, awesome. So who is registered or subscribed to the channel? I want more hands at the end of the session. Cool, so I've been working on content from my own perspective. So I've been writing my blog, tweeting, and I've been writing a book. So last year I released the VDI design guide, and in that guide I completely describe the process of designing a VDI, obviously, or logically. But a VDI nowadays is different than it was 4 to 5 years ago. 4 to 5 years ago we designed a VDI and it was mainly based on Windows 7, sometimes had GPUs, well, quite common. It was running on traditional storage instead of running on vSAN or Nutanix or something else, so HEIs. And nowadays stuff is completely different. So from a security perspective, I heard NSX already being touched quite some time. NSX security is part of how we deliver a VDI nowadays as well. And like I mentioned, GPUs is part there as well. So Windows 10 currently expects a GPU. And I've been a big fan of GPU. So the GPU section in the book is I think almost like 70 pages, and it completely describes the way you need to use a GPU in the variation of use cases. So when talking about GPUs, who still remembers this GPU? Who had it? Which one was it? The what? Voodoo 1. I don't have, well, I can give you like almost an empty glass of water, but you should get a giveaway for this. It's a Voodoo 1, the Monster Voodoo 1, and it was the first card that actually shown what offloading specific tasks to a specific piece of built hardware could change in the way you have user experience. So which game is this? Quake 2, who's that? Quake 2, this is Quake 2. So this is based on software rendering. So your CPU and your RAM are kind of emulating what a GPU would do with it. So enter or insert a Monster 3D card, and bam, this happens. No one is amazed. And that's not weird. So sure, textures are a bit different. If you look at the gun, you know, the textures are somewhat more smooth. But the biggest difference in playing this video game was the latency decrease. So anyone who plays first-person shooters? So what does latency do to a game? It kills you. That's basically it. So using a card, a GPU in this case to offload specific tasks towards that GPU just lowers your latency. And latency in general, and you all know that from a VDI perspective as well, is something that needs to be as low as possible to have that great user experience. So we leap ahead like 20 years. Last year, a couple of colleagues of mine and some help from NVIDIA, and who saw this the playseat last year at the UC TechCon? Who played with it? Couple of hands. So what we did, for anyone who doesn't know, we took playseats, we took hardware, a GPU, Horizon, so Blast Extreme, and one of the cheapest thin clients we could find. And what we did is we were able to get like a gaming PC experience to a thin client and Blast Extreme, running an F1 game over 60 frames a second. But why would anyone do this? Well, why would you jump in water without a cage and be surrounded with sharks? Or build a dance floor in a minivan? Or jump out of planes? Climb Mount Everest? I just heard someone say, just because we can. Is that right? That's it, just because we can. If you would like to see the results of this project, on my blog I released a post about a month ago, and it completely describes all challenges we faced. It shows a couple of movies, including one where you see Brian Madden, who was our guest keynote speaker last year, drinking beer while driving and hitting the F1 car in a wall. Well, which concludes that you should never drink and drive, even virtually. But let's go back to the project. So the project, Customer X, Industry X, is a type of customer that has been gathering and processing data for, let's say, the last 20 to 25 years. And that data is becoming more and more important for the way they do their work. So imagine you have big piles of data and you need to get specific information out of that data. Nowadays, you would have data scientists working at that in that customer to process that data, to get the analytics you need to, for instance, stay ahead of the competition, or to get medical information, or to get any type of information that could give you a head start comparing to the competition, or to help people. Well, imagine those data scientists 20 years ago being men with angry men with beards. I would love to have a beard like that, by the way. They were working on ancient computers, ancient data centers, long before I was born. I'm from '82. This doesn't look like '82. I would guess somewhere 78, 77, something like that. And they were doing that on like the first Intel CPUs, the 4004. Anyone from before '82 who remembers this CPU? I see one hand. Cool. So they did that on ancient stuff. But if you compare the data that they had back then and the calculations they did back then, and compare it with the enormous amount of data we have nowadays and the complexity those calculations take, they're using massive data centers right now to do the same thing they did 25 years ago. Who knows which data center this is? Right, so, oh, yeah, see, same hands I saw last time. So this is the Mare Nostrum supercomputer in Barcelona. Whoever is planning to go to Barcelona for VMworld this year, make sure to visit it. It's built in a church. It's completely OCD compliant, so every cable is attached in the same way with the same color, so it's like an IT admin's wet dream. And the interesting thing is, so this complete data center is filled with NVIDIA GPUs. And there's a big benefit in that. So let's hope this works. It does, awesome. So what you see here is image recognition. So take those big piles of data, in this case being images. Those images are being recognized through a Skylake CPU running an image recognition software or solution called TensorFlow. And as you can see, by doing that through CPUs, about 4 to 5 images a second are being recognized, are being analyzed, and being labeled. In this case, flowers. So let's run it again. You see, it's detecting the type of flower, and it's doing that around 4 images a second. Now imagine what would happen if you would do the same thing with the GPU. We take an amount of images, and by using TensorFlow, TensorRT on a GPU, you can see we could do around 800 to 900 images a second, image recognition. This is an example of how data scientists nowadays are able to process data in a much higher pace, in a much bigger amount than they did before. And the reason is that we have CPUs and GPUs, obviously. The architecture of these two are similar, but they are completely different at the other side. So a CPU has a number of cores, let's say, in this case, 16. And these 16 cores are really, they're built to handle any type of calculation. So a CPU, an x86 CPU, should be able to run any type of workload. VDI workloads, calculations, you name it, playing games. And these cores are really complex because they need to handle any type of workload. Take a GPU at the other side. These have thousands of cores. So take a modern Tesla CPU, a GPU that could have over 4,000 CUDA cores. And these cores are less complex and really good at doing something, a specific task, such as image recognition, such as, I'll come to that later on. If you would like to know more about the difference between CPUs and GPUs and how you could use those in, for instance, a mixed environment, check out the latest Lightboard video. If you just Google ITQ Lightboard Niels Johan, you'll find it. Cool. So let's go back to the project. We had a couple of requirements. One being, we must be able to run all applications on any type of device. And we need to do that from any type of location. We needed to have 99.9% availability for all use cases. And just, so I already mentioned the data scientists, but we also have researchers. So they have complex applications that analyze data. Data scientists do analytics on data as well, but on a much bigger and bigger scale. And we have normal users, like using a browser and Windows 10 and stuff like that. So we needed to have 99.9% for all use cases. And we needed to create the best UX, user experience possible for all of those use cases. And that's what makes it complex. Because have data scientists at one hand maybe fully utilizing a GPU and normal users at the other hand trying to do the same, mix them on a single platform, and that's probably where you could create a shitstorm. But I'll come to that later on as well. We didn't have a specific requirement to lower a TCO, no, we didn't have a specific budget constraint, but we needed to lower the TCO, so the total cost of ownership, where possible. And that gave us the first idea to mix all of those use cases on a single platform. From a use case perspective, so we have the data scientists that on a previous or in a previous situation used high performance computing clusters. Who's familiar with who's not familiar with HPC instances? Right. Think of a server rack full with hosts and a queuing engine in front of those hosts. And that queuing engine is just distributing tasks towards all of those nodes. And what an HPC cluster is really good at is distributing complex calculations throughout that whole cluster and getting the result much faster back. We have the power user, the data science of the researchers, which are true power users, and we have the normal users, which use the browser. From an application perspective, data scientists already have kind of modern applications, containerized, utilizing GPUs. AI technologies might be part of those applications. Oh, and also based on Linux OSs. So these power users, they have, well, their Windows OS, their complex research applications, photo viewers, collaboration software, and also use a GPU. And normal users that use a browser have access to badly built WebGL applications. And whoever has worked with VDI in combination with WebGL applications, so what would happen if you won't add a GPU to that profile or to that session? Does it work? Does not work, right. So if you combine, or if you are looking for something that's common to all these use cases, it's the GPU. Right, and if you look at resource consumption, we saw that data scientists are doing 95% reads because they're reading a lot of data and doing analytics on that data. Power users have like 40 to 60 read to write ratio, and normal users have like the opposite of data scientists. From a CPU perspective, all is kind of normal for a mixed environment. So you see that the data scientists require multiple cores but a lower clock speed. Power users, like every power user, need a high clock speed, and the normal users can work with normal resources. From a RAM perspective, so these completely stand out, 64 gigs versus 8 gigs versus 4 gigs. And from a GPU perspective, and this is where it gets interesting, data scientists require a lot of GPU power. And the power users kind of, and the thing that they have combined is that they require CUDA. And CUDA is a framework to do calculations on a GPU instead of just displaying images. And the normal users just display images. So the challenge here was, how can we consolidate 3 completely different workloads on a single platform without any challenges? And to basically comply to all of the requirements we had. Well, I'm an architect and I love How I Met Your Mother, so the challenge was accepted. And the first thing we always do when engaging in a new project is to run an assessment. And an assessment gives you all sorts of insights. And in this case, the thing that was really interesting is that the majority of users are just working between 9 and 5. 9 and 5. Almost 100% of those users are working between 9 and 5. And if you look at the resource consumption, they're quite stable. So, from 9 to 5, for 40 hours a week, those users are consuming resources. Which also means that for 120 hours a week, I have resources available. So what would you do with a crap load of resources? Cha-ching! Well, we also know that the power consumption nowadays is, or power usage is really expensive. So in this case, creating my own cryptocurrency wasn't the best of plans. But yeah, we chose to combine those resources on a single platform. So we came on with the following concept. Yes. Just before the day starts, we create a bunch of desktops. So as soon as users will start connecting towards the platform, they'll get the desktop assigned. During the day, we'll just, upon request, create more desktops, so enough desktops will exist for the users to work on. And before the end of the workday, we'll start to consolidate those desktops to less hosts. So we'll free up a lot of resources. And what we'll do then is spin up so-called HPC workloads on that same platform. And we'll spin them up so the data scientists are able to run those workloads that require a lot of compute power and GPU power at night. So they just schedule those tasks and run them at night. So they'll run all night, and just before the peak hours commence again in the morning, we'll do the same trick we did at the beginning of the night, again, but the other way around. So we'll consolidate the HPC workloads to less hosts, spin up a load of desktops, and make sure that the users are able to work again. And the whole thing just repeats every 24 hours. Obviously, we found some challenges along the road. So if you basically look at the architecture a little bit, we have use cases, we have different types of applications, we have different types of OSs, so both Windows as well as Linux OSs. We have an infrastructure based on vSAN and GPUs. And we have obviously Horizon, vCenter, and VROPs to manage VMs. And we need some form of automation to be able to script and deliver VMs. So we use VRA, Power CLI, and Puppet to do that. And this is really important. So we utilize the power of microsegmentation of NSX to ensure security. Data scientists with data that's privacy sensitive shouldn't be accessed by a normal user accessing a browser and YouTube or Facebook or something like that. So hence microsegmentation. So in terms of challenges, one of the first challenges we faced was that HPC workloads may never be interrupted during maintenance. So imagine you being a data scientist. You start up a task that could easily take up 12 to 15 hours. And because of maintenance, the host you were running the task on is being shut down after, let's say, 10 hours of working time. Me, as a data scientist, I would probably be kind of pissed. So up until a couple of years ago, or 1.5 years ago, we didn't have a solution specifically for this because a VM that runs those tasks requires a GPU. So vGPU vMotion was introduced about 1.5 years ago. So who still remembers the first time you saw an actual vMotion, a normal vMotion? Was that awesome? It was like magic, right? So whoever witnessed a vMotion with a vGPU enabled VM being transferred from one host to the other? So who didn't? Who has never seen that? Right, so I'm going to try to create that vMotion moment again. So I'll show a demo of a vGPU vMotion. I'll connect to a virtual desktop in my lab. I'll play a YouTube video, log into the vCenter appliance, and execute the actual vMotion. And if all the demo gods are with me, and I hope so. Hey, Tron! Yes. Fingers crossed here. I ran the demo a couple of times before today. This camera, by the way, is not to take pictures or as soon as the blue light starts blinking, you should be worrying. Okay, so we have a desktop. Right, so I'm connected towards my home lab. Here is a YouTube video, which I'll play. And the bandwidth is kind of not the best, but let's see if I could type blindly. Dit is Arbo compliant. Right. Nope. Right, so signing in. Awesome. For sake of the resolution, I'll just enlarge this a bit. So I have a VM called YOLO. I'll explain later on why. And YOLO is running on ESXi 3. What I'll do now is migrate YOLO to right. Yeah, resolution does suck. Correct. E6i2. Yes. And do it with high priority. Awesome. Okay, now take a look at the video. So the vMotion is being executed. It's being copying data right now. Over 10 gigs. The image freezes a bit. Couple of seconds. Well, it's 4 gigs of frame buffer being used right now, and it continues again. Is that awesome or what? So I have a piece of hardware connected towards a VM. In a host, I have a host at, well, the other side, having the same piece of hardware, and the VM is being transferred from one host to another through a piece of copper, or fiber in this case. And that's awesome, right? Without a user having a bad user experience. So let me quickly finish this demo. Yes, and hopefully go back to my slides again. Right, so this is what we all saw. Do you know why the glitch? Well, the answer is there, but there is a glitch, and the biggest reason for that glitch is that the speed of light sucks. So, who knows who this guy is? Right. That is John Carmack. So who knows who John Carmack is? He wrote a book. Well, he wrote multiple books, but the thing he's most common for, or most famous for, is creating God mode in one of the most awesome games ever, which is Doom. He created Doom, Quake, I think even Wolfenstein. So this is John Carmack, creator of Doom and Quake, and nowadays he's CTO of Oculus. And the reason, well, you know, the speed of light does suck, but and obviously he wasn't, this quote is taken from his book or his autobiography, and sure, he wasn't talking about vMotion in that book, but it's the same thing. So if you, again, are playing games, and you're playing games locally, everything's being rendered by your GPU, and you need to take data from a server that's in the US, and you're playing from IJmuiden, that latency could kill you. And the same thing is here with the vMotion. So because of the latency, we aren't able to create a smooth transition yet. I've heard that they are working on it from a VMware perspective, but for now it's from a VDI perspective. It is what it is. From an HPC perspective, there's no challenge because the calculations will run anyways. And that is where vGPU vMotion was originally created for. Having a VM, a Linux VM or a Windows VM, calculate stuff that needs to be transferred to another host because the host itself, where it was running on, needs to be taken out of because of maintenance. The VM is still able to run that calculation. So your data scientist will still be happy. Right, next challenge. vSphere hosts licensed by VMware Horizon may only run virtual desktops. So anyone who's working for VMware, please close your ears. Guys, I'm probably going to tell something that I'm not allowed to. I should have added a disclaimer to my slides. Right, so take a VM, a normal VM, or well, better yet, take an HPC VM. So this is the anatomy of an HPC VM. We see CPUs, RAM, disks, and networking. We add a GPU with cores and frame buffer on top of it. So frame buffer is the physical video memory of the GPU. We add an operating system, in this case Linux, system agents such as VMware tools, and a container engine, in this case Docker, NVIDIA Docker, to run specific NVIDIA containers on top of it, such as this one. So the TensorFlow demo, or the TensorFlow which I mentioned, is an an application that runs in a container like this. So the image recognition software, the flower recognition software is an example of such an application. So I'm not allowed to run that on a host that is just licensing, is licensed by Horizon, and thus is only able to run virtual desktops or servers that service that virtual desktop, such as my connection server or a SQL database that my event or SQL server that my event database is running on. So I'm not allowed to run that machine unless, boom, you install a Horizon agent on that same machine, and suddenly it's a desktop. And because of the power of Horizon, that has all sorts of cloning technologies, I'm now able to clone that machine as well. So if I need to spin up a gazillion HPC instances, Horizon is able to do that. And there was another benefit of this, because we can now offer those data scientists remote access through Workspace ONE, since we are integrated Horizon with Workspace ONE and applying conditional access to those machines. So instead of just giving them SSH access from outside the network, we can now just leverage the power of Workspace ONE to give them conditional access, remote conditional access to those sessions, which is totally awesome. Right, so next challenge. Scaling up and down needs to be as fast and automated as possible. And I already mentioned cloning. Well, if you look at the requirements, the technical requirements we had specifically for that solution, we needed to have Linux OS support, because most of the HPC instances run on Linux. We need vGPU support for obvious reasons. We needed instant cloning. And we also wanted LDAP integration, because if you provision a Linux machine, it's convenient to the end user if you could just sign into the Linux machine through his AD credentials. So when looking all this up in the release notes, we found out that Linux support is there in Horizon 7.8. vGPU support is there. Instant cloning support is there. So LDAP support was there as well. So happy camper, right? Yeah? Wrong. Because although all these features are supported, they're just not supported in this exact combination. And since there is not a solution to this problem yet, the thing we just changed is to go back from instant clones to full clones. And because we are leveraging Linux as the base OS, which has a really tiny footprint, cloning a VM by using full clones takes just a couple of minutes. So still, we're happy in this case. We're hoping for instant cloning to add all of this support as well. And yeah, we'll see what just happens. Maybe anyone from VMware could elaborate on that. I see a certain Spencer Pitts nodding. So we'll see what happens there. Cool. Next challenge. Some HPC apps are not fully utilizing GPUs, and I need to run a little bit faster through my slides here. So we take the HPC VM. We have CUDA or Tensor enabled runtimes, such as the image recognition framework that directly talk to the GPU. And if you take a virtual desktop, so this is an HPC data scientist desktop, that is a virtual desktop for my power users. They have different types of applications, modern and traditional. Those modern applications leverage the power of top. Modern research apps leverage the power of CUDA and Tensor as well, so that's quite easy. You could offload all of those calculations to the GPUs, what they're made for. But traditional apps don't have that specific feature. So traditional apps will talk to your CPUs and RAM, and as you probably all know, that will negatively impact your density. So the more apps can directly talk to a GPU, the higher the density becomes on your platform. That's eventually what you all would like to achieve. This isn't something that we just can solve overnight, so we're busy in an application migration and rationalization project and phase, and hopefully migrate all the traditional apps towards modern apps in some point in time. But obviously that takes time, like any application migration phase. So yes, I'll skip this demo. What I was showing is the demo of the big bald head, but I have a much more fun demo lined up, which I would like to show instead. So the big bald head, the only thing it shows is that my home lab is powered by Intel Xeon D CPUs, so the low power, low voltage Xeon CPUs. And the bald head is partly being rendered and partly being calculated. So lighting within the head is being rendered. If you would like to see the demo, check out my session. I did the same session on the VMUG earlier this year, and I showed the demo there as well. And you can see perfectly what the result is of running complex stuff on a cheap-ass CPU, enabled or supported by a GPU. Right. What I do need to do now is quickly start the other demo, because that will take a couple of minutes to run. Connectivity does suck a bit. Right, so here it is. So the camera light will start blinking in a minute or so. Let's hope it will continue. Cool. Okay, so CUDA. We're not going to do that. So most apps, and this is definitely something I would like to talk about. Most apps don't have support for multi-node HPC instances. I already explained what an HPC node is. So it's on average, it's a queuing manager or queuing agent that distributes tasks towards multiple machines, multiple VMs in this case. So you need a solution to enable distribution of those tasks, and one of those solutions is Bitfusion. So what it does, take your host with your GPUs, take your TensorFlow app to recognize data, take Bitfusion FlexDirect as a service broker in the middle of it, and what happens is that Bitfusion Direct talks to all of those GPUs that are being distributed throughout your whole platform. And as soon as the TensorFlow app starts requesting requesting calculations, it just distributes those calculations towards other hosts. The challenge with Bitfusion is it's insanely expensive, and it requires a shit ton of bandwidth. So about 40 gigs minimum between those different hosts. The advantage of Bitfusion is it's any application that is able to talk to a GPU can be distributed through Bitfusion FlexDirect. So there's an alternative called Horovod. Kind of does the same. You take your TensorFlow app, but instead of having a different framework, the runtime of Horovod runs inside your application and is able to distribute those calculations directly to the hosts. Bitfusion is open source, so it's Horovod is open source, so it's completely free, but it's only able to do so through modern applications. As a result, if you do that, we take the image recognition process again, and instead of recognizing around 800 to 900 images a second, what you see there is Kubernetes, so the Kubernetes load balancer. And as soon as you spin up the number of nodes that could recognize those images through Kubernetes, almost 7,000 images a second could be recognized. Imagine this being working at a hospital and you need to process big tons of data. This would be really helpful in this case. So this is one of the reasons why we mix those workloads on the same platform. So demo time, and I still have 4 minutes. Who knows who this guy is? Come on, people. One, Silicon Valley. Who has never seen the Silicon Valley show? Okay, go home now Get an HBO account and start. This is probably one of the best series ever made. It's a comedy series, and it kind of shows the whole process of inventing something as a startup and being acquired by a big company, and it's really funny. This guy made an application called Seafood. So it takes a picture of food and it sees what kind of food it is. So it uses image recognition, kind of like TensorFlow. Right, so it is able to detect if an object is a hot dog or if it's not a hot dog. That was it. Cool, right? Now, so what it basically, is the light blinking? Is it on? Blue? Awesome. Okay, so it does image recognition, but it does it on really, well, it recognizes a taken picture. What I would like to show in my last demo is a TensorFlow application that is freely available. It's called YOLO. You only look once. And what it does is, if you have the right hardware, a GPU, you are able, am I able? I'm not able. Yes, oh, you see stuff happening here. You were able to detect objects around 20 frames a second in real time. And I could just wave around the webcam and you see a chair and a thinker. It isn't able to detect DeLoreans yet, but this is cool, right? We have a lot of persons in the audience, so that's good. Cool. Right. So let me quickly kill the demo and finish up the presentation. By the way, this demo, so the camera is connected through Blast Extreme, redirected over camera redirection in my session, and processing the data through Blast Extreme as well, which is obviously not the average use case, but hell, it works. Right, so we did the TensorFlow stuff. To wrap up, conclusion. Multiple different use cases can run on a single platform, but you need to take care of automation and stuff like that. TCO, because of that, TCO can be lowered. Everyone knows that the TCO of a VDI can be a challenge if you don't take the right parameters and requirements into account. So by doing that and basically talking to the business, because we found this out after we already commenced the project. So I was already talking to the business because we needed to design a VDI. And along the way, we just found out that more people were interested in a single platform with a shit ton of GPUs. So along the way, we just found out that this was a really good idea. Automation works, but it needs some more maturity. To give you a tiny heads up, because I'm going to change my presentation a bit in the near future, we're going to do stuff with VRA and probably provision desktops from a VRA perspective and just add them to Horizon, which in that case automation does work a bit better. Buy licenses after designing a project, because hypothetically, if we didn't have license already, I would probably acquire stuff like PKS and distribute containers from a different management component. And just include vGPU enabled containers from that perspective, which totally makes more sense than doing it by Horizon. But this is a really cool project, and because it does work, the customer is satisfied. So that's good. And yeah, finally, VDI just still rocks. Cool. So, any question? We probably can find a stapler somewhere. Yeah. No questions? Cool. Enjoy the rest of your day. You can find my details here.